In this lab, we will look at projectile motion. It's important that we first remember that when we analyze this trajectory's components, they are independent of one another, but their combined effect gives us that curved path when we throw a ball, or in this case, a steel ball, is thrown out. We don't consider air resistance, meaning it's under the influence of gravity only. Within this lab, we will look at calculations of velocity at which our launcher will shoot the ball to calculate and predict the final position depending on the three distinct angles we position the launcher in. We will be looking at these formulas more in depth in future slides as well. This recent paper introduces a hybrid deep learning model that basically learns complex patterns from a larger um, set of historical data that doesn't necessarily rely on traditional mathematical models. And really, the purpose of this hybrid model in the context of military warfare was to improve the prediction of projectile trajectory as well as its duration. Of course, our lab focuses on ideal projectile motion in terms of our experiment. However, real life considers much more complex factors and dynamics, making this type of modeling very interesting and innovative. Those who are fans of watching basketball have a good idea of projectile motion and how it works. For example, a player might not be super conscious of the physics behind it, but they must launch the ball at a certain angle, usually around 45 to 50, with an initial velocity to ensure that the ball does go through the hoop.
So the materials that were used for this experiment were a mini launcher, and this was used to load a marble-sized ball to be launched and distance to be measured. A marble-sized ball, which was launched. A meter stick was utilized for measuring distance in meters between the launcher and the place of landing. A paper was used for the purposes of documenting the land of each launch ball, and a laboratory notebook used for the recording of observations and results.
For our lab number 6, we use this mini launcher. It's labeled as in this diagram. One is our first metal weight. So using that when it was dangling, we set it to either the protractor, which was 2 right next to it. And that would help us determine the angle. So our first thing was having it at 0 angle, so completely horizontal. And then from there, we would increase the angle from 30 to 45 to 60 to find the rest of the information for this lab. Um, Also, the launch point is where we would insert the little steel marble. We inserted it to the second click. In the video, you had saw that as we inserted it, we used a pencil to insert it further. And as it was going further inside, it would lift the metal hook. And depending on the clicks that the hook lifted, showed how far in we had put it. We always set it to the second level. And that's how we started our experiment. That also showed like a range setting. So the deeper in, the farther or the more powerful it would be for it to be launched out. And then our lanyard was just the string that we used to pull to launch the steel ball.
For the procedure, we first calculated the muzzle velocity by establishing the cannon at a completely horizontal position. We pushed the steel ball inside to the selected range and pulled the lanyard and let it go. We did this a few more times while also using a plane sheet and the carbon sheet to measure the distances before using these values to get the muzzle velocity we would use for the rest of the experiment. Then we set the mini launcher at 30 degrees and measured the vertical position before using That, along with the muzzle velocity to calculate initial velocity in each direction, the time of flight, and our final theoretical position. Once finishing those calculations, we launch the steel ball 5 times, average the values, and calculate the percent error. After that, we repeat these steps for angles 45 and 60 and calculate the percent error between the theoretical and experimental values.
So as we had explained with the Canon and then in the video how we had started our experiment, we had to ensure that the metal weight landed exactly at the zero on the protractor. The Canon's bullseye on the side of the mini launcher is where we put the metal marble. And then this is what we use to establish our zero, the zero of our position coordinates that you'll see in the next slide. And that's how we started building this lab. That's a picture of our first 5 launches from the Canon. It was 5 in total. The first one is very faint because we had the paper flipped incorrectly. And so it did leave a mark, but not as dark of a stain. Once we realized what we had done, we flipped it, and then the 4 other tries were exact. So after we had done our 5 tries, of course, the paper had to be put in front of the Canon. We did measure using the meter stick to measure from where the Canon ended. Like the Canon was on the edge of the table, so from there straight down, and then from that on the floor all the way to where the paper was to where the first marks landed. And that's how we got the 1.810 meters, 1.820 meters, 1.824 meters, 1.825 meters, and 1.815 meters. So we found the average, we added them all up and divided by 5, and our average was 1.819 meters. And then that is equal to our XF being our final position. And then this just has the rest of our information of the 9.1 meters is the distance from the floor, from where the Canon was on the table to the floor. From the floor to where it actually landed on the paper was the 0.91 meters. And then using that information, we calculated our time to be 0.431 seconds, using that formula of the square root to yi over the negative ay, and negative ay is our gravity, which was negative 9.28. And then from there, we used our time to find our VM, which was our velocity, our muzzle velocity, the VM, which is also equal to our Vx, which is the initial velocity of 4.22. So this is the table we had started with, and then using the measurements or the average that we got from the distance when we first launched the 5 times, we averaged it out, and then this is just our table with our full information that we got from our formulas. And then this is just a table where we put the information we had got once we calculated our muzzle velocity using the average and then using our time formula. And from our time formula, we found our muzzle velocity, which was the same as our initial velocity. After those steps, we started our experimental development. And that's when we set the mini launcher to a 30-degree angle. And then using the Vx, we had calculated the initial velocity in each direction. So it was the initial velocity or muzzle velocity times the cosine of the angle, which was 30 degrees. And then again, the same thing, muzzle velocity times the sine of our 30-degree angle. So for those, we got their Vx from the cosine was 3.65 meters per second, and then our Vy from the sine was 2.11 meters per second. And as we continued our experiment, we started with the 30-degree angle, which is the one right there in the middle, and then went to our 45-degree angle and then our 60-degree angle. So our 60 degree is the one on the farthest right, and then our 45-degree was the one on the farthest left, and our 30-degree angle was right in the middle. And then we did the same process for all three, the 30-degree angle, 45-degree angle, and 60-degree angle. We used the equation that A equals half of A, so it was the half of 9.8 because that's gravity. Our B was our Vy, which is 0, and then our C was our Y0, which is the distance from the ground or from the floor to our cannon. And then this is just a table that shows our different heights. So the 0.95, 0.96, and 1.77 as we move the cannon up. And then that just shows the 9.81 times the 1/2 equals the 4.9. So after using that formula, xf equals Vm and cosine of the times time, we found our theoretical distances was 0.29 meters, 0.975 meters, and 2.36 meters. From there, we found our experimental differences, our delta x, and then ideally it would have been 5 launches for each angle, but we only did 1 launch for each angle because we only had a certain amount of time for the lab. So using the single launches rather than the averages, because we only did 1 launch, we got the 2.4 meters, 2.29 meters, and 1.77 meters. Using that information in our delta x experimental differences divided by our theoretical distance times 100, we got our percent error.
In this lab, we investigated the motion of a projectile launched at different angles to study how gravity affects a curved path. So we used a mini launcher. We measured the horizontal distance traveled by the steer ball at different angles and compared the experimental results to the theoretical predictions, which we got using the kinematic equations. And the goal was to determine the muzzle velocity of the launcher and analyze how changes in the launch angle influence the projectile range. And overall, this experiment demonstrated the independence of horizontal and vertical motion and how those combined produce the parabolic trajectory observed in projectile motion. So, going into the questions, where do you think percent errors come from? The percent errors come from like small measurement inaccuracies, air resistance, and slight variations in the launch angle or velocity. Do you think there are factors affecting your experiment that are not considered in the formula we are using? So yes, of course, air resistance, launcher friction, and small variations in height or angle are not included in the formula. Which ones? The main factors are air resistance, uneven surfaces, and inconsistent launch speeds from the mini launcher. And are they significant? Yes, they're significant because even a small difference could greatly affect it and change the range. Do you think there's a way to minimize this error? So, errors could be minimized by doing more trials, securing the launcher firmly, and measuring the angles and distance more precisely, like taking the time. And all your percent years equal? Why or why not? So no, because a higher angle means a longer flight, which increases the effects of air resistance and small errors. That's it. Thank you.